Yeah.
Oh, yeah. Okay. Thank you.
Okay. Okay. Well, if anyone joins, let them in. I won't be able to see them.
Yeah. Oh, you cannot see? You can see?
No, I won't be able to see. And just so
yeah, I will
make sure
put it in a way. I will put in a screen so I can see somebody coming on. Okay. I don't put full screen. If I don't put full screen, I can see somebody.
That's a good idea. And yeah, just make sure they're on mute or whatever. But okay, so find that. What? Oh, let's go back to yours. Okay, so can you see that?
No, I saw for a minute. Now it's off.
Oh. Oh, okay. That means I have to do. How does it work?
You had it correctly. Only thing, because it showed you as well as the screen, which is the correct way. I mean, which is.
This is the way you're seeing it now, is it? You're kind of seeing it now.
Only you, yeah. I don't see any presentation.
Oh, okay. Oh, right. I see what happened there. Sorry.
All right.
Today
is. Take your time.
Yeah. Okay, so let me start again. Share.
Okay.
Okay, so
yeah, it's okay now. Oh, it was okay. Now it went off again.
Oh, okay. Completely off. Yeah. Can't see anything.
Now only I can see only you.
Right. So I think they might have changed the setup for this PowerPoint thing. And I can't remember how, because, well, actually, we had this problem before. And
you go to present. Share screen, it should work, right?
No, but I mean for the slideshow.
Oh. Okay, you have to put that slideshow on. Then you have to put it on. Put the presentation. If you don't put the slideshow on, I think it will not do that. So you have to and then put share screen. Something like that, I think.
Yeah. No, that won't work, but yeah.
It's on the side. It's on the side of the PowerPoint. I had the same problem. It's you cannot go full screen. You cannot go full screen. So then you cannot do the present things like that. So you have to do. Let me check. Yeah, you have to do on the side.
Oh, like the way like the way you were seeing it at the beginning.
Yeah, on the top it says there are two ways you can do slideshow. One of them will not work, and the other one will work. Yeah,
so that means there's only one way.
Do you see the two screens?
Yeah. Okay, you can see this now.
Yeah.
Fine. Let's go with that then.
Yeah. Okay.
Fair if it was like full screen, but we'll just do this. So, like if I were to hit present live, it's just going to go off, isn't it? So there's no point in doing that.
You can try.
Okay. It went off.
Yeah, it's going off. Yeah, it's gone.
Okay. What's going on? Okay. Yeah, now it's gone in doing some crazy stuff. And back.
Yeah, I can put on my PowerShow and see how I did that.
Yeah, give it a go there.
I try to go there and find out. I have to pull up a PowerPoint.
Technical difficulty.
I can try. I mean, there are a lot of quarks in this one. It's not perfect by any means. Yeah, let me go with this one.
Maybe you just hit present. I think that's it. So at the top. Yeah, because there's also a button in the thing called present. So if I hit that, what about now?
You see,
it went off again.
Nothing. Nothing.
Okay, so that's not so yeah. There's just one way to do it then, and I thought we had it.
Let me see.
We had done it
previously.
Try
my thing, how it works.
Yeah, we could do like full screen share, but maybe not. You know what, Rajan? I'll just present it the way it is, and we'll figure it out later.
Yeah.
Okay.
I'm trying to see from my point of view. I'm testing.
Okay.
Yeah, that's fine. Oh, now
right. So this is it. So the title is Anamorphic. So I've changed the title, in a sense, or the name of the research from unique hyperspheric model to anamorphic universe model, which can be an acronym. You know, you can anachronize it. That's not the right word. What is the word where you
what is that?
What? Oh yeah, sorry. Yeah.
The other morphic you mentioned?
This is So I've changed the title of the research from unique hyperspheric model to anamorphic universe model.
Ah. Okay.
So yeah, I'm pretty sure there's a way to present this properly, but I cannot remember how to do it. So you know that where you have you take the first letter of each word, so it creates this AUM, which there's a lot of it's not called an anachronism, but I've forgotten the term for it. Kind of like an abbreviation, but it's not. There's another word for it. But there's plenty of physics models with this abbreviation AUM, but hopefully this one will be more successful because I don't remember what the other ones are. So the objectives of this talk are to create a three-dimensional stereographic projection of the universe using SDSS data, to rotate the sphere then by 180 degrees in the XZ plane to invert the universe, or to turn the universe inside out. Through this show, sorry, what?
Yeah, I cannot really, because it's first of all, I'm using half screen so that I can other people, and secondly, you have to do this way, so I cannot. Can you zoom in somehow?
Yes, so there is an issue.
Oh, John Hodge is coming, I think.
Okay, cool. Maybe hi, John will be. Hey, John, how's it going? Maybe John will be able to. Oh, wait a second. I can zoom a bit, yeah?
Yeah, that's good.
But then it is it doesn't fit the screen if I do that. So and now it's slightly smaller. Ooh. John, do you remember how to present these slideshows? We're kind of drawing a blank on how to make them. Don't hit share. And we don't, because if I hit slideshow now, it's gonna stop working. What you could do is download it and then present it in numbers. That might work. I'll give that a go.
Custom chart for beginning. Go. I'm doing that. You go to the screen. Let me try one thing.
Yeah, you have a go there. And in the meantime, I'll download this. So, John, how are you keeping anyway? How's mountain life? Oh,
well,
yeah. Can you hear me? Oh.
So everything. Are you still in the mountains?
But
you can get internet now.
Hello, John? Oh, you're sharing. Okay.
Can you, can you see now?
Yeah, I can see you're presenting something.
So
it's not technically a slideshow, so.
Oh, sorry. I should have. This goes where it's long breaks. I mean, stop screen. That's not what I want to. Let me see.
Okay, this might work better.
I was looking at some NASA.
Okay, I think I figured it out, Rajan. Yeah, we can start.
Okay.
Now. Okay. Hopefully,
I have to go
there's
to Windows. You can get okay. I have to go to Windows.
Yeah, hopefully there's no other technical issues with this, but this should work. So, okay, so it looks like some of the text may be different.
Yeah, it's okay.
Different font, but it won't be a big issue. So this is it. So the anamorphic universe model, we went through that slide. So this will show how the universe began, how it will end, how long did it take the universe to form. We'll look into the quasar paradox, the size of the universe from a four-dimensional perspective, 4D stereographic projection of the universe, again using STS data. Other similar models to this one we'll look at, and talk a bit about simulation theory, leptogenesis, and finally support vector machine learning analysis. Might be a couple of other headings in there as well. Also missing the title here for objectives. So that's a bit annoying. I'll probably have to highlight all the titles as we go. 3D stereographic projection. Here's an example of a unit sphere, let's say, projected onto the tangent plane. We can see that the grid lines on the sphere get distorted as they're projected onto the tangent plane. So the point at the top here, the zenith, will be projected to infinity. And each of these square grids, therefore, will get bigger as they go out, logarithmically, I guess. And so then if you rotate the sphere, you'll see that the grids kind of warp and transform. So this is a type of Mobius transformation, and that can be produced using special linear 2x2 matrices. Is that it? Oh yeah, so this just tells you how to download the STS data that I'm using in the current research. So you get the top 1 million galaxies from Dior 17. You get the object ID, the right ascension, declination, Z redshift, and you have it, less than 17. So you can get all this from sdss-server.org and kind of run these queries in there. Yeah, this is just before we do start working with SDSS data. It's good to have kind of a toy model to work with to begin. So we have, to begin with, we start with the untransformed grid metric. So this is just a grid formation, and this is it again in blue. When we rotate it, so this is projected onto the bottom of the sphere and then rotated by 180 degrees, which means that the points in the center go to infinity and the points around the edge become this kind of inverted square. So that's what we're going to do with the universe to turn it inside out. We'll have the stars here. Well, actually, technically, the universe is already inside out, so we're going to turn it back in the other way. Yeah, and then you can rotate it to project it out this way. So here's an example of the unit sphere again with all of the galaxies from the SDS, database projected onto the unit sphere, and then rotated by 180 degrees, and then you'd reproject that back. So I'll give you a look at what that looks like. So this is the universe as it appears at the moment. The Milky Way galaxy would be in the center there somewhere. And then we have the first Great Wall, and then consecutive Great Walls outside of it. And then when we rotate this by 180 degrees and project it back again, so this is like at the center now we have infinite space effectively. The first Great Wall is now like a halo around the entire universe, and the Milky Way galaxy would be at a point in infinity in every direction in this universe. So how did the universe begin? Identifying the singularity. Yeah, so again, we can talk about the hyperspheric model moving from the 3D model that I just showed you to a 4D model with, instead of the unit sphere, we'd need a unit hypersphere of 4 dimensions. But we can inscribe a tesseract within that to make it easier to understand. So in the inner cube, at the very center of that will be the Milky Way galaxy, and that can be described as our local space. Then we have the interstitial cubes around that, which are, I think there's 6 of those. Yeah, 6 of those. And then outside of the cube will be, oh yeah, within the interstitial cubes, there is our local groups. So generally blue shifted galaxies. And then outside of the cube, projected outside, stereographically projected, I mean, will be the rest of the universe, everything else. So let me just read what I've written here. Inner cube, yeah. So when we rotate the inner cube out, all of the stars outside will get rotated in, and but the interstitial galaxies will stay in place more or less. So what I'm suggesting is that at the beginning of the universe, all of the stars were galaxies were in the center, and they rotated out. And then at the end of the universe, they will rotate back in. So in order for that to happen, all of the stars and galaxies in the universe would need to become smaller and bigger as they go out. So we can look at the scaling factor needed to do that. Here's the 4D stereographic transform. So we take, hang on a sec. So this includes the rotation and the scaling factor, which we can see is 70. And this is the equation for the backward transform. And then you just reverse it to get the opposite way. So that describes how the universe began, because you're scaling it up by 70. Oh, this doesn't appear to have it. Oh, it does have a title. It's just over here. So we can rescale the universe, as I was saying. If we have an equatorial projection, so we're projecting to z equals 0, we need a scaling factor of approximately 7,000. But a much better way to do it is to use z equals -1. So we're placing the Milky Way on the south pole of the hypersphere, essentially, and then projecting. And so for that, we need as I said before, a scaling factor of 70. 70 is very close to the value of the Hubble constant. which is around 70 kilometers per second per megaparsec. So we question if this is a coincidence or if there's something meaningful behind it. So I looked into the concept of Hubble, well, Hubble constant, or no, the Hubble tension and doubling time, that's correct. Because there's, as I mentioned before, obviously we have a number of different values for the Hubble constant. From the CMBR measurement, it's around 67. Tip of the red giant branch gives us 70. And the distance ladder is around 72 to 73 kilometers per second per megaparsec. So if we look at the rule of 70, which is used to calculate the doubling time of things like investments and population growth, we see that the exact value for that figure is 69.3, which becomes the rule of 69. That can be rounded up to 70, and then a convenient numerator, so to allow for different divisors, is the rule of 72. So I would suggest that possibly the correct value for the Hubble constant based on this is around 69.3, but rounding it up is perfectly valid, and also having this convenient numerator could also be useful, so something to consider. One thing to note, though, is that when we talk about an exponential growth of a quantity, something needs to already be there in order for that growth and doubling time to exist, which is possibly why the Big Bang model, as it currently stands with a singularity, might not be. Oh, one second. Right, might not be. How could it be correct? Because you're not doubling anything. There's nothing there at the singularity, essentially. Like at the beginning, there's no space and no time, so it makes it a little bit more difficult. Exponential growth in the number 24. Now, so in another slideshow presentation by Bayes, he spoke about Edward Lucas, who challenged his readers to prove if you have a square pyramid of cannonballs that contains a square number of balls only when it has 24 cannonballs along its base. And there's the equation to show that. So we see that the end result is 70 squared, and this is kind of, I'm likening it to exponential growth, but we see that the number 24 becomes important here. So the expansion rate of the universe. So this is what we're trying to figure out from the initial dense, all of the galaxies being squashed into the inner cube of our inscribed tesseract. How long does it take for it to expand out to become the size of the known universe, which appears to be infinite? Since we have this number 24, we can ask, well, and we're thinking about time, is it 24 weeks? Is it 24 years? But then when we think of time and the number 24, the most obvious one is hours. So I decided to use that as my base reference frame. So when we do that and apply this equation so that it scales to 70, so in hour 1 it's this, let's say in hour 2 it's going to be slightly bigger, up to this, to the 24th hour, and that will give you the end result of a scaling factor of 70. But each of these obviously comes out as different numbers, which can be seen here: 1, 2.2, 3.6, and so on, all the way up to 70. And there is the graph for that and the equation to produce it. Okay, so one issue that you might consider is that when we are rotating the entire infinite universe back into the central cube, because there's an infinite amount of galaxies stretching out to infinity, that when we rotate it back in, it would cause a singularity, which we're trying to avoid for obvious reasons. So what I did was I plotted the top 1 million galaxies with this is actually 1 million galaxies. So we can see that Milky Way again is at the center here, and then we have a dense area here, and then it drops off precipitously around 2 or 3 radius. And then things get a lot quieter right there. And so we could ask, well, what's the reason for that? Is it because, you know, all the stars and galaxies in here are blocking our view out here, so we can't pick up as many, or the project hasn't been running long enough for us to pick up all of these galaxies that are out here? You just need more time. Or is it that this is actually how the universe is, and that further we look out, the more and more spread out all the galaxies we get? That is my prediction, is that is what is going to occur. And this resolves then the problem of the singularity. So when we rotate it back in, because it's exponentially dropping off in terms of stars, there's no issue when it's compressed and rotated inside. And the only thing you do see is a slight dense part out here, but that could be just an anomaly in terms, because there's another great wall that goes out around the edge there. So it could be just a denser part, because also from previous research that I've done, I showed that the great attractor is up here. So this area will be more dense anyway. And the great repeller is down here. But we're not going to go into that too much in this talk. So we can look at the rotation of the universe and ask, as I mentioned previously, if there is a denser part here and a less dense part here, is the contraction of the universe already occurring? Like eventually all of the stars will squash into this area and then move into the center again and be rescaled by a factor of -70. So we can ask, is the process already taking place? Is the universe already moving towards the rotating back in? And I would argue no, that it's not, based on what I can graph and model. So according to this, the universe appears now as up here, and this is the universe after pi rotations, so 180 degrees, and this is again the universe after pi rotations, with the cube after 2 pi rotations. So basically what this tells us is that the universe has undergone pi rotations. So it is exactly 180 degrees rotated out from the central cube. But as I mentioned here, this assumes that it has undergone pi rotations to begin with, because it could have undergone slightly more, slightly less. So the proof here is basically tautological and not really very useful for that reason. So let's look at a few other things that might be a bit more useful. You can look at expansion, because the universe is said to be expanding, possibly even accelerating, although that's being called into question now. And then time dilation. So this will offer a solution to the discrepancies between type 1a supernovae and quasars as well. But let's look at expansion first. So I'm arguing that based on this model, universal redshift cosmological expansion is an illusion. And I think this picture probably explains it better than maybe other scientific diagrams might. We have in the center here a drawing of a man who has had some influence on promoting yoga in the West, but I thought it was a nice image, so I've used it. So basically you can see that this is like an example of anamorphic perspective, and as we can see that as we get further away from this cylinder here would represent the center of the universe, with the center of the cylinder being the Milky Way. And then as we get further out, we see that things are distorted, you know, shapes appear bigger and so forth. So this kind of distortion, not this exact one, but from the stereographic projection model, could produce distortion, anamorphic perspective distortions, which could be interpreted as redshift, and then, or well, it would create the redshift, which could be interpreted as expansion. But I'm suggesting that's not actually happening. So again, from the perspective of time dilation, here we have the Milky Way galaxy. We go out, things get more blue shifted compared to the rest frame of the universe. And then after zero redshift, or Z equals 0, we see that the universe begins to exhibit redshifts again. So for the galaxies, compared with the rest frame. So I'm suggesting here that since the first Great Wall, everything that's projected outside of the if you recall with the inscribed hypercube, everything that's outside of that cube is the universe. But I guess I kind of said this already, but so this would be the outside is equal to redshift, positive redshifts in a sense, and this is the blue shifts where we have the interstitial cubes. And then I'm suggesting that in the Milky Way we should have no real observable redshifts or blue shifts, just from relatively speaking, essentially. Okay, someone's also called time dilation. An interesting fact about the cube now. Yeah, so this would be the universe here on the hypersphere, and this is the tangent plane. So when we look out into the universe, it's flat. So we have the metric is the same all the way along. But in order for this to, when we reproject this back onto the sphere, we're going to get a logarithmic compression of the metric. If we assume, as we rightly should, that the speed of light is constant, it will be constant on the hypersphere because that is probably the real reality I'm suggesting. But as it travels through each of these metrics, when it's projected back, you can see that the distance between A and B here is a lot smaller than the distance here, these being equivalent A and B on the sphere and on the tangent plane. So if the light is moving at a constant speed through here, when it's projected onto here, it's going to be moving much faster, which means that time needs to be moving slower here compared to in here. So when we get to the North Pole up here, time is going to be at 0. And I think that is basically what I've explained here in other words. Oh yeah, well, so I think that an important point is that when they're looking at quasars or not quasars, sorry, as type 1a supernovae, they can use them as like not standard candles, but measurement devices for the slowdown rate, time dilation as we go further out from the Milky Way, looking further look back times. But what we will notice is that they suggest that this is because of the expansion of the universe, and it could well be, but I favor this model that it is to do with the stereographic projection from the hypersphere. And of course I would. Okay, so quasar redshifts. Well, the difference between the this is getting into Holton and Arp's work, so John might be interested in this part as well. Quasars have large cosmological redshifts, indicating that they are very far away. However, Holt and Arp discovered that there are many quasars associated with nearby galaxies, such as this one. And there's the quasar there. But there's a bridge between them, so these must be on the same level, even though they have, very different types of redshifts. So you can see there. Yeah, so it's clear then that quasars have anomalous redshifts, and this hasn't been explained by current standard model of cosmology. So I'll have to explain it today. Just a bit more about type 1a supernovae and quasars. like we say, they both have similarly large redshifts. However, supernovae have time dilation approximately 1 divided by 1 plus the redshift. And this seems quite similar to the equation used for stereographic projection, but I have to look into that a bit more to prove that one way or the other. There's various reasons. So it appears that the supernovae have, and the quasars both have very large redshifts. But if we look at the time dilation for supernova, well, which indicates that they should be very far away. If we look at the time dilation for supernova, that falls off with the distance, you know, or increases with the distance, I should say. But we don't see that with the quasars. Ergo, quasars are nearby, but then we still have to explain the anomalous redshifts. Current plausible explanations include gravitational redshifts from black holes that are, you know, either nearby or in front of the quasars. Although I don't subscribe to that because I think it's a bit too coincidental. So again, I think the current thinking on quasars is that they are black holes. So what I'm suggesting here is, like, if we think of the hypersphere, we're kind of turning the hypersphere inside out in this image just to understand what's going on a bit better. We have these would all be quasars, so they're all distorting space-time in a very pointed manner, as you can imagine, because they're black holes. So, but the point of the light source is at you know, the north pole of the hypersphere. So if these things are pointing inside the sphere, they're going to be closer to the light source, the projective point, than anything else on the surface of the sphere. And so, as we know, if we move something closer to the source of light, it appears bigger when projected. So I'm suggesting then that this kind of redshift, this anomalous redshift that we're seeing with quasars, is more akin to a shadow being projected from four-dimensional space. So the conclusion here is that quasars are nearby in tangent space, but further away in hyperspace. And that's not a very descriptive conclusion, but hopefully I'll make it clearer in the next couple of slides. So we can look at it's kind of going out there a bit, but you know, you can think of, if you have one quasar black hole stretching out into the center of the hypersphere and another one, they could plausibly join up together, which would create the possibility of wormholes connecting vastly different areas of the hypersphere, which is interesting possibility. Be difficult to know how to detect these. You know, you could say maybe you'd see extremely redshifted celestial objects in a straight line, or possibly gravitational lensing, but it's really not at this point. So this is just a visual explanation of what I was talking about earlier. So you have the galaxy here with its companion quasar, and the galaxy is on the tangent plane, so on this surface. So its shadow is exactly equivalent to its size. But if we move the quasar closer to the light, its shadow is going to get bigger, and move it further away, obviously, it gets smaller. So that is, oh no, what happened here? Okay, we're missing all the data for the size of the universe. Maybe I don't know where that went. What I'm going to do is switch to the other one, because you can't see that. So I'm going to stop and start again. Share screen. I'll just check where that is. Yeah. And is that it? where were we? We were down here somewhere. Okay, so this is different calculations for the size of the universe. I can zoom in on this a bit if you need to see. Okay. We're using angular size distance with a Hubble constant of 70 again because of what we mentioned, and the universe has to be flat because, as we said, the tangent plane is flat. So the inner cube length is 2,530 megaparsecs, with the sphere diameter then is 5,600.8 megaparsecs. And the total volume of the hypersphere is 202 trillion gigaparsecs to the power of 4. This is an estimate based on the projection of the inner sphere onto the tangent plane, so it's not exactly correct. It would lead to a slight distortion, which would increase the values ever so slightly. So this would probably have to come down. There could also be errors, some small errors in the, because we're dealing with four-dimensional geometry. It can be a bit tricky to get the correct sizes for, you know, radii and diameters and circumferences and things like that. I'll just continue on here so that we don't have to switch back and forth. But this is an example of an anomalous galaxy from Holton Arp's work, AUM 205 to 221. So the redshift for the companion E, which is the quasar, is this value here. Now, if we should, you know, the average diameter of a quasar is a couple of light day, a few light days. So we just take that average and convert it into megaparsecs. We have this value here, and then basically by using the equation for the light, the size of the shadow based on the light, we're saying, oh no, sorry, actually in this example, we're basically taking the difference between the z redshift of the quasar and the galaxy and taking it as a percentage, and then using that same percentage to increase the size of the quasar to this value here. And so then we have the diameter of the hypersphere, which I mentioned before. So then to get the distance, we need to take the size of the original size of the quasar before expansion and divide it by the shadow. And that gives us a distance of 0.5618 megaparsecs. So that is the distance that the quasar has to be inside of the 4D hypersphere. So that is essentially, that is quite large, because if we think of like a star with maybe 10 solar masses that collapses to a black hole, that is going to create, what is a Schwarzschild radius of about 45 kilometers from the event horizon to the singularity. But here we see that in actual fact, from a 4D perspective, we're talking about a much, much larger distance. So again, this is interesting because when we're talking about, what are they, wormholes and stuff, you know, be traveling very fast distances or very large distances, but also very quickly because of the, as I mentioned previously, with the speed of light issue, that light travels faster as you go up the metric. So it's it wouldn't be an issue. You can travel vastly faster than the speed of the light as further you go up the hypersphere. Let's get into the 4D stereographic projections, like the actual results. Can you, yeah, oh, sorry. Right. So this is when we convert the STS data, three-dimensional STS data, onto the hypersphere and then reproject it back. these are the kind of images we get. We can see that this is an 8-dimensional coordinate system because we have 4 hyperspheric coordinates, 3 tangent space coordinates, and 1 identity coordinate, which is the projective point at infinity or at the zenith of the hypersphere, either one. And that point is common to all of these, to every point in the universe, essentially. And then we can just, this is just a few examples of some different galaxies, celestial objects from STS with their right ascension declination, Z redshift, and then the 7 dimensions used to locate them in space. But we really only need, well, 3 and then 4 for the further, you know, so it's these 4 on the hypersphere and then 3 on the tangent plane. Zooming in a bit on our previous image that I showed, you can see that the Earth is at the center, or well, the Milky Way galaxy and the Earth is at the center here. And then we have these anisotropic shells of universes called great walls that are surrounding us. So this, you know, obviously suggests, contrary to what Milner said, that the universe does not appear to be isotropic and homogeneous, same in all the directions. So that's an interesting point to consider. Then when we rotate all of the stars, rotate the hypersphere and reproject, this is what we get. So now infinite space is at the very center of this sphere. This is the kind of diffuse area around here is the, how do you say, is the first great wall of galaxies. And this would basically project the entire Milky Way on to infinity. So for example, if the Earth was the center of the universe, then it would literally surround the entire universe. It would be absolutely enormous. And then obviously the center of the Earth would go out to infinity, which would be interesting. So the center of the Earth would in effect be larger than the entire universe. This is just an example of rescaling again. So we take all the stars, the blue stars that we saw before, not the turned inside out ones, but turn it inside out and scale it down by a factor of 70, and it'll fit inside of the space at the center, is what this graph is attempting to show. Wondering, should I switch back to the other one? Was it bigger? Do you guys, would you guys prefer if I did that? Hang on. Won't take.
I think it's okay.
Okay. Well, hang on a second. Okay. And share screen. So Rajan was just saying that I think the sizes were a bit small or something for the text. So, okay, so we moved on to there. So this is similar theories. Where did it go? Oh yeah. Obviously, there are similar theories such as de Sitter space. Basically, what that's describing is that over time, as entropy takes hold, space empties out, and everything goes to infinity essentially. And so universes with positive cosmological constants, lambda, and less matter become a de Sitter space. So de Sitter space is linked with entropy. And also it's something called the holographic principle, because if everything can go out to this surface, then it can be projected back in. So this is very similar to what I'm talking about. Although de Sitter space, as I just described it there about cosmological constants and less matter, appears to have been disproven, although it's still quite popular with a number of astrophysicists such as Leonard Susskind and others. But the reason why it's disproven is because that kind of geometry used by Friedman and stuff does not actually create the topology of space. Another similar one is the anti-de Sitter space with conformal field theory. This is an interesting one, but it is essentially a toy model where you have hyperbolic space, and then you have a conformal boundary on which special relativity can take place. So you can map particles out here which map to gravitational fields in the center. The reason why it is a toy model is because, as we can see here, the gravity is inverted. It's getting stronger towards the edge and less strong in the center. So that's why I guess they consider it a toy model. You could fix this toy model in a sense by taking the hyperbolic tiling and coordinate transform it so that it goes into this, you know, the strong gravitational distortions are happening at the center. But the problem with this then is that your central point here becomes infinite, and yeah, you could reproject that back onto a back into hyperbolic space and then stack those, and then you would no longer have a toy model, you would have a correct model, I think. More similar theories would be the metric universe. Gerd has been speaking about this. This is his model, of course. So we have the hypersphere here, and then the event horizon and the particle horizon. I'm not entirely sure where they are located in this diagram. This could be the event horizon. And then the particle horizon would be here, maybe. So, yeah, but there are differences between the metric universe and de Sitter space in my own model. Specifically with the metric universe, I'm not entirely sure. Oh yeah, well, one major difference between my model and Gerd's is that Gerd is using a space-time manifold in a sense, so that the hypersphere has space and time all combined inside it. So my model does as well, but in a very different way. Like for me, that the model is there, but time's still just running like it's not a direction in space, I should say. Okay. Okay, so this kind of leads us into simulation theory a bit, because with the logarithmic metric I described earlier on the hypersphere, obviously what that's doing is it's like file compression, information compression for the universe. So, you know, we ask, is the universe infinite or is it finite? Well, it is infinite on the tangent plane and finite on the hypersphere. So basically, the great expanse of it is an illusion. Now, obviously, there's space surrounding the hypersphere as well, which could go on for an infinite space. So ultimately, the universe would be infinite in some sense, but not in a way that we can access. Oh, well, except we can on the tangent space. But so really, we're saying that all the infinite information on the tangent space can be compressed onto the hypersphere, which makes it quite handy and could suggest some kind of simulation theory and simulator. So we're kind of getting into more speculative stuff about matter and antimatter, the leptogenesis and matter-antimatter asymmetry, but I'll walk through it anyway. So if we take a 4D transformation using the, or just a normal, so that in this case we have matter written on one of the faces of the inner cube, and then when we rotate it out, we see it's backwards. So this is kind of my analogy for matter being on the inside of the cube, and as it rotates out, it becomes antimatter. So let's see if I can prove that in any kind of useful way. If we look at a positive electric field, let's say the field lines are moving out from a central point. The negative electric field, they're moving in. So if this was at the center of the central cube, all the lines are moving out. But when you rotate it out and stereographically project it, now all the lines are moving back in, although there will be a space in the center. So these are just some of the equations used to create the field, and these are the corresponding components of the vector field, which are used here. So this just shows how to invert the field. Like I mentioned earlier, we not only have to transform the vectors, but also the metric, which is what I showed you at the very beginning anyway. We also need to make the vector fields negative, but you don't have to do that with the 4-dimensional case. So, well, yeah, and then this kind of describes how if we track one of these vectors before and after transformation, we see that it flips across here before inverting. So this is a mirror image reflection, which is interesting because it's what is expected of antimatter in the charge parity symmetry. So the thing I'm suggesting here is that there's an equal amount of matter outside of the hypersphere as there is inside. So matter antimatter asymmetry could be resolved in this case, which means that when the matter moves back into the center at the end of the universe, the scaling factor will reduce it in size, and it will also possibly reduce in density because the metric is getting larger. So it will become much smaller. It's just it looks like there's more matter out there than there actually is, or else you could say there is more matter, but that through the transformation process it will become less, and that amount of matter I'm suggesting should equal what's in the inside. But all of that is very conjectural and probably quite wrong. We'll look at a support vector machine group. That's just a joke, you know, support groups. But and specifically hyperplanes and decision boundaries. So this was an interesting concept. When I was working with Rajan, I was asking him to come up with the metric transform, I think, from a general relativistic perspective of the original metric out to the stereographic projection metric. But obviously it was kind of a fool's errand to begin with. I really shouldn't have asked him to do it, but because there is no time-space metric in my model other than maybe the logarithmic metric on the hypersphere. But as I said, that's not exactly the same thing as what Einstein's talking about. But a good thing did come out of the discussions is that Rajan suggested that I use support vector machines and kernels, you know, to find I think it was to find the decision boundary between the two different objects so that you could decide how to transform them. But yeah, I thought that idea was so good that I just had to try it with the two different classes of galaxies, the ones that are squashed inside the cube and the ones that are projected outside the cube. So these are the results of that work. We can see all the galaxies outside, then projected back in, compressed, and a zoomed in version shows that the decision boundary, or the hyperplane, is behind the first Great Wall of Galaxies. And that was a really unexpected result, because what that means is that these galaxies here are on the surface of the hypersphere, and they don't move anywhere. So when all of these galaxies compress towards the great attractor, excuse me, let's imagine the great attractor is up here at the top. They all compress and then they move in. These galaxies here will stay on the they will not be affected, just like the interstitial galaxies out here. Only what's at the center, which is our galaxy, will be obliterated by the in-moving galaxies. So if we were looking for any safe space to potentially colonize in future, it would be all of these guys here. Now these will move and transform as the universe rotates, but wouldn't be nearly as catastrophic. Although there's a good chance that there's enough distance between all of these things that maybe, you know, everything won't be eradicated. Like the Earth could still survive because it's quite small, and as we said, that the density drops off by a large factor, and we're not dealing with all of the matter in the universe being compressed into a small space. It's going to be a lot less dense. You know, there's other factors involved. Also, I'm considering the fact that, you know, I'm saying this might be antimatter out here, but when it rotates back in, it will become matter again. So there's no issue there. It wouldn't be a complete obliteration or anything. Missing antimatter. I think we kind of looked at this, but oh yeah, so this is like just harking on about as above, so below, same amount of matter in the inner cube. It's basically, I've already discussed that multiple times. So the conclusions are the universe can be modeled by matter projected from 4D hypersphere to a 3D tangent space. The Hubble constant is related to the rule of 69, 70, and 72, speculative. And the expansion of the universe as determined by the cosmological redshift is an illusion brought about by anamorphic projection from the hypersphere. I believe that to be the case. Time dilation is caused by the constancy of the speed of light when projected from the logarithmic metric to the tangent space. Yeah, I would agree with that. The universe took 24 hours to expand to its current size. So that's kind of funny, really. I mean, it's a bit of a joke, but I mean, is it? I don't know. You know, the 7 days of creation, and God took like an hour to create all the stars, or not an hour, sorry, a day. So it fits in with what's written in the Bible. Also, the number 70 is really important in the Bible as well. I think I'm not sure, but yeah. Anyway, the number 70 appears repeatedly throughout the Bible. Every point in the universe can be described by at least 8 dimensions, and I say at least because when we're talking about the light that's streaming through the projective point, you have to ask where that light is coming from. It could easily be projected. You know, it could be like a pinhole camera situation where it projects out the other way as well to a second hypersphere above it that projects onto another tangent plane, which would therefore give you a total of 15 dimensions. The 4-dimensional volume of the universe this is wrong because unless I fix that. No, that is wrong. I think I said it was 202 trillion gigaparsecs to the power of 4. The universe can be turned inside out by rotations of the hypersphere without singularity. Redshift of quasars and lack of time dilation indicates that they are projected nearby, but their gravitational field situates them closer to the projective point. Antimatter on the outer cube, matter on the inner cube. Leptogenesis solved? Question mark there. And the 4D hyperplane decision boundary is located behind the first Great Wall of galaxies. That ends my presentation. Thank you very much. Yes.
Great.
Okay. So does that help a bit with the understanding of what I was trying to get across previously, or do you have more questions? Answers?
Yeah, there are a lot of things there that sort out. But I think one of the things, I think John will probably expand it more. But what I had is a couple of questions only right now, and then I will turn out to John, who was the more extensive things on these galaxies and all. So the one question I have, when I'm looking at it, I'm not sure. I have to read back. So I'm analyzing what happens on the hypersphere versus what happens in tangent plane. And I'm using a general thing about the hypersphere is curved. So I can use like a Ritchie tensor for the general relativity. And the hypersphere is more like Lorentzian transformation. So which means that it is inverse of what you're saying. So hypersphere, I don't know whether it's limited by the speed of light, but on the tangent plane, I think it'll be a constant speed of light.
Yeah.
Which means that the distance may be much larger. So it is larger because when you project on your tangent plane, everything is spreading apart. So if it is moving at the speed of light, the universe
will be much technically, yeah, I mean, the speed of light is not invariant on the tangent plane. It speeds up as it goes further out, but time slows down. So it is constant. Yeah, sorry, continue.
Yeah, so it's not a Lorentzian transformation. So if it is speeding up, can we use Lorentzian transformation? If it is speeding up?
Well, I mean, surely it doesn't matter. You know, you could have like a variable speed of light or variable time, and both are interchangeable, aren't they? So
yeah, that's the hard question. The time dilation may be a a quark in the way you use the time versus the space.
Well, when I say that, though, I am saying that from a objective point of view, like light is speeding up on the tangent plane, and so time is slowing down. But I think from a mathematical point of view, you could probably switch the equation back and forth. It wouldn't matter.
Yeah, I'm looking at the clocks themselves. Like I said, there are 6 types of clocks I'm looking at. Maybe that will resolve the issue, but that's more complex.
I don't know if there's an issue there, though. I mean, have you identified an issue that needs to be resolved?
Yeah, the sense that if you use different types of clocks, like we use one clock, and then the group. No,
what I mean, just in terms of the model I'm proposing, like what I'm proposing there is not a I'm not suggesting that this is a problem that needs to be solved. I'm just describing what would take place with this model.
Yeah.
And I think based on that, you could solve problems in cosmology. Like, for instance, you can explain why there's time dilation with type 1a supernovae, for example. You know, and then you can even go further and tentatively explain why Holton-Arp's quasars are, you know, just as redshifted as these supernovae, but are linked to nearby galaxies. So, yeah. So I think that the purpose of this model is to resolve the crisis in cosmology. It's not suggesting further crises, although I'm sure there will be more. So if you can identify them, let me know. So it would be interesting to me.
Yeah. Other aspect I think is about topology. Something you mentioned about topology. I think the topology of the 4D hypersphere versus when you invert it, the topology, is it invariant topology or variant topology?
Well, I'm not sure. I mean, you know, when you hear relativists talk, cosmologists and these people, they always talk about conformal transformations on a sphere and stuff. And you're going to have that with this because it is a sphere, perfectly conformal. So, you know, technically all of like the local distortions for Einstein's general relativity, that's all going to work fine. In fact, it appears to be necessary. So it looks like the hypersphere is not like a smooth orb or anything. It's bumpy, you know. It's got little galaxies and stars, and they're all creating these bumps. And then the black holes, if you will, are like far in there, you know. I mean, well, it could be that you see, like, let's say you have a star that's like embedded deep inside the like, let's say this is the hypersphere. It's embedded quite deep. If the compressed metric goes down, it's going to be like at a certain level. So the speed of light is going to be higher where it is. And so light could actually exit the gravity well because it'd be moving much faster. And as it goes down, the gravity well gets less intense, speed of light gets less. And the star could like, boom, you know, just project itself right into space, even though it's like 0.5 megaparsecs away. It could be like right there, you know. So let's say our sun is a black hole, let's say, then, you know, as you approach it, it would take like a really long time to get to it. It's actually, it could, if it is a black hole, it could be like much further away than it appears, is what I'm suggesting. So that could kind of rewrite general relativity a bit and maybe some other aspects of. So, you know, but these are just ideas. They're fun to play around with, and we'll see if the maths works.
In that sense, there's no singularity.
No, there is a singularity, but it's just really far away. I mean, I know what you mean. Yeah, in a sense, there is none, but yeah, it just suggests like the sun would actually be much further away than it appears to be, but in a four-dimensional direction we can't see. This could resolve some of the odd things about the sun, though, such as why I think the temperature, if you go 50,000 kilometers from the surface of the sun, the heliosphere there is much hotter than the actual surface of the sun. So that could be possibly explained by event horizon kind of something. I'm not sure, but I'm just kind of thinking about it. But then there are other gravitational anomalies that can be resolved by this model, which I didn't go into in the slideshow because of time constraints. But there's, I'm sure you both heard of the, is it when I think it's a lunar eclipse? No, a solar eclipse, sorry. I think it's a solar eclipse, so it could be a lunar eclipse, where you have the pendulums on the Earth. And then as it occurs, it causes the pendulum to swing slower, I think, something like that. So this cannot be explained either by Newtonian or general relativity, Newtonian gravity or relativistic gravity, if you like. But it's plausible that it could be explained by this model because, you know, where is the fourth dimension? Well, you know, by that I mean the fourth spatial dimension. We can't see it. So where's this projective point? Well, it turns out that we can actually point to it even in the tangent space. It is in every direction you point to, no matter which direction you point to, you are pointing at it. And it is at an infinite distance away. So that means that all of this light from this projective point is streaming back into the universe and creating like planet here, sun here, you know, galaxy over there. But if two of the let's say the sun, the moon gets in between the sun and the Earth, those light rays are still like projecting the Earth, projecting the sun, projecting the moon, and then projecting the Earth. So it has to go through now 3 separate kind of instances of different objects. And so that could have an effect on something like a swinging pendulum. I don't see why it wouldn't. So that could possibly explain that anomaly. Basically a glitch in the system is what it appears to be.
Yeah, the conformal theory is very similar to, I think, is it Roger Penrose? Somebody is suggesting that conformal. Yeah.
Well, Roger, yeah. I mean, well, Roger Penrose has a number of different theories about cosmology. I think his biggest one, I've forgotten what the name of it is, but it's something to do with, you know, like a repeating universe, like not a big bounce scenario though. Cyclic universe, yes, thank you. So it kind of goes into the anti-de Sitter space, essentially. Everything just goes away to nothing, and then it starts over again because it can't be nothing. That's a very interesting theory. I like it, but I've always liked that theory. But it just, yeah, so, but he does mention, he actually does talk about stereographic projection and conformal, you know, transformations on the sphere. He mentions it in passing. It's not a huge issue, but he's looking at it more from a quantum mechanical point of view. So talking about what is it? I think it's maybe SU2 rotations for fermions on the sphere somehow, and how it's all linked to his twistor theory. So basically, you can take any point as a direction in space. It is part of his twistor theory or something like that. But yeah, he's not using it from a cosmological point of view, I don't think.
Yeah, other aspect I saw about the variability of light is light get transformed. Like it go, you know, they are all the same thing. Like it becomes phonons when it goes through a matter, then it converts back to light. So it can actually slip through, you know, a very dense matter, but it converts itself into a different form.
Yeah, yeah.
You know, the electromagnetic thing, now it becomes phonons and it travels through vibrations, and then it comes out, and again it becomes light. So if you look at that too, it depends on how we are looking at here and there. The light has traveled through that at its faster speed of light, but it could be a transformation of the different forms of, you know, the same electromagnetic wave in terms of phonons, photons. So that's a unified theory. I mean, we are still working at it.
Well, yeah, that's interesting. Keep it up. Yeah. Sounds like there could be something there. I mean, are you saying that when the phonons go through the molecule, for example, they're moving faster than the speed of light? Or?
Gravitation. If there is a gravitational field involved, the gravity field can be much faster, right? So it is.
Well, yeah, I mean that's true in my model, because you have the point at infinity, the projective point. These rays are coming down, and they're projecting what's on the hypersphere onto the tangent space. And in order to do that faithfully, it has to be happening instantaneously. So these light rays are there's some kind of different form of light. I'm suggesting that's kind of inverse. Instead of electromagnetic, would be magnetic, electro, you know, something like that. And it's a torsion field thing that's giving the that's allowing it to be instantaneous. So, and then because it's like firing into the tangent space and into the sphere, maybe that's causing some sort of deformation, which could therefore be characterized as gravity. Therefore, gravity is an instantaneous force from the top to the bottom, but it might be speed of light on the surface, you know, horizontally, speed of light, vertically, instantaneous.
Thank you very much. I'll turn over to John. John may have many questions or clarification. He might tell us.
No, John's normally quite. But what did you think about the Halton ARP thing, John? Actually, I have questions for you.
The whole what?
You know, because I remember from your research, you talk a lot about Halton ARP, right? And his research.
Oh yeah,
You mentioned it often enough, so it was,
yeah.
So it's interesting that you know, I was sort of introducing those topics here today because you came back. So yeah, I was just wanted to get your opinion on that, and maybe even, do you see any connection between your model and this in terms of sinks and sources? You know, I mean, I've been kind of thinking about it, but they are very different models.
Well, I don't know. Your model. Oh yeah, what you're doing is describing where things are.
Yes.
Are you describing any cause?
What do you mean?
Are you describing any cause?
Like a cause for things.
You mentioned, yeah, you mentioned things rotate to get them out from your center.
Yes.
Is that a galaxy rotation or a universe rotation? Actual? Meaning,
well, yeah.
Looking at angular momentum and that kind of stuff?
Right, yeah. So I'm just looking at technically it's the rotation of the hypersphere which takes it out. And then the projection allows it to be outside.
Right. So do you consider that real?
Yeah, I mean, it's interesting. Are there real forces involved, or are there maybe fictitious forces? See, this is it. Yeah, I mean, on the force side of things is interesting. I think there could be a lot of work done on that, because obviously when you're talking about like cosmological constants and de Sitter spaces or any of these kind of theories that use general relativity, they're all about gravity and the mass of the matter in the universe that can potentially either draw everything back together or be pushed out by some cosmological constant. And really, in this model, such an idea wouldn't work, because let's say we have the hypersphere and we have everything on it. I don't think that all of that mass will contract the hypersphere. But I mean, it could start like flowing down to the bottom, a bit like what you were saying before about how all the junk in the universe falls to the Earth, you know? Like the Earth is at the south pole of the sphere. Everything could move towards it. But I don't think so. I think that's not likely. These are, like, if you remember the diagram of the de Sitter space, where it's like, it kind of goes in like this and then goes out. So there's no singularity in de Sitter space either. And so that's kind of what I'm describing. You have the mass of the universe is there at the beginning. It expands out to become the universe as we see today. And then later on it rotates back in. And that is that is the exact same geometry of that what do you call it? Like conic section or whatever.
So what I'm interpreting here is that you don't look at energy like general relativity does.
No, only in a local sense. Like for the quasar black holes, that kind of thing, you could start bringing energy into it and discussing how much that is deforming the hypersphere. Locally, yes, you can have energy and deformed space-time, or space at least, but with some amount of time in there because of the metric issue. But on a more universal global scale, no, I'm not going into that at present anyway. So it's just very much. But I think to be fair, like while it is descriptive, I think it also accounts. It does bring cause into it a lot. You know, there's a lot of things or aspects that are considered crises in cosmology, and this system that I'm proposing provides the answer to why those things are the way they are, which is in a sense causal. I think possibly, maybe not. Maybe my definition is wrong.
You know, the Penrose thing you were talking about before, the cyclic universe. Part of that cyclic universe theory is that the universe currently is contracting.
That's right. I heard that. Yeah, I think you may have mentioned that before. I've been thinking about that.
Close to what you were talking about.
Well, yeah, there was the idea that the local universe appears to be contracting, right? And that the expansive universe, the apparency of the expanding universe outside of that is well, as I
recall the Penrose thing, he was talking about in general relativity. If the universe in total is contracting, it matches general relativity with experiment much better.
Oh, okay.
I think that's the way it was being phrased.
Yeah, I haven't heard that.
I don't know. That's
the precise thing that he said, but I don't know. I mean, there's the other idea, I think it was a Wigner, and I think Christopher Langan also came up with it, and he came up with it independently, but maybe 60 years later, 40, 50 years later. And then I also kind of came up with it, but I think at that point it doesn't really matter. But the idea that is the metric of space expanding, is the universe expanding, or is matter contracting, which would be a covariant transformation. So it wouldn't matter either way. They both appear the same thing. But in fact, in my model, it's kind of more in line with yours in this sense. The universe is completely static. There is no expansion. There is no contraction. It's just an illusion because of the projection from the hypersphere. That is the only thing that I think can explain it. It's static, but
so how do you?
But dynamic as well, because there can be these rotations of the hypersphere and other processes that can cause. I'm not going to go into it today, but there are physical forces and such that I can reference in terms of the end of the universe, and how that's going to come about, and what speed. There's some new physics involved in that, though, that I won't go into today because it's too lengthy, really, to describe.
Mm-hmm.
But interestingly enough, it has a lot to do with what Rajan's been talking about over the last couple of months. So I find very interesting. I think, Rajan, you have some sort of source that you're pulling your knowledge from, and specifically what you're looking at with gradients between strong and weak gravity is bloody fantastic. And this is the whole thing that I'm talking about will hinge on that. So I will be able to describe what the strength of the weak gravity is, what the mass of that particle could be possibly, and also, yeah, I mean, all of this information seems to come from a specific source as well. So I think I can identify your source by name in the future. Not going to do it now either, though. So
in a larger sense, it could be like, it oscillates between entropic and energetic universe. It could very well be that way, in the sense that I'm right now thinking a large model where entities form, like a hot PDP mechanism. So it's superluminar, but the entities form from that, like condensate, and the entity is entropic. But the environment itself is energetic. So it's an entity within environment in general. So that is the final resolution. These are the two objects. And the entity is entropic, whereas energy, the environment is energetic. So it flows into the entropic, but it becomes larger and larger. So there is a finite size when it becomes larger than certain size. Again, it disintegrates, and again it forms small part, like rocks or smaller and smaller things. Because I think it's a balance between volume free energy and surface energy. We see in nucleation, like I study in material science, nucleation growth, same thing happens. Like small nuclei, you have a large surface area, surface volume, surface energy also. So then, it has to convert to bigger and bigger. So the volume free energy start increasing, but when it becomes equal, and then normally because of dynamic aspect, the volume free energy tends to be larger than, because of the dynamic spread, it goes over like a pendulum, so it becomes larger than the sun. So again, it tries to reduce that, and in that way, it becomes fragmented. And so you have fragmented places, and these fragments again, so it goes through this kind of like a cycle, but so you have a creation and an annihilation or a growth, and also a fragmentation and a growth aspect always continuously occurring. So that's where this weak gravity, strong gravity come to picture, because if you have, that's interesting, because I believe that each object has its sphere of influence. It spreads its density matrix. So, so it has larger density matrix interacting with the smaller. I think in one of the CJ Pass paper, I bring out this one. That So the larger thing, so they coincide, and when you look at the vectors, they're always, it seems attractive, but it's you can think of a magnetic analogy where actually they repel. The two things come together and they repel. But they will appear as if they are gravitation. If you work it out, you will appear as if they are always, centric attraction is there. But if you look at the details of the quantum gravity, it's actually because they are coming together and then they separate. And it depends on the center of gravity, things like that. So if you adjust for that, you will see that it's actually the matter colliding with each other, small particles, and then moving away. But it depends on, the geometry. So that's where the geometry aspect comes. And your 4D, now you calculate the volume of the 4-dimensional. How do you calculate the volume? Like a toroid, I don't know what shape it is, hypersphere.
Oh,
but the volume is not same as the 3D, right? I mean, it's more complex.
Well, this is it. So the way you remember the graph where, well, there's a number of ways to do it. Like with the decision boundary, so you can have that as the surface of the hypersphere. You could also have, where the flux distance, where it goes up, and then you see the red shift on one side and the blue shift on the other. That graph. That's also the boundary, which is set at 0, so that the decision boundary. So then you can just work out the distance between us and that boundary, which is about, equivalent to 0.5 redshift, which works out at around 1265 megaparsecs. So then once you have that, that's the radius of your hypersphere. And then from there, wait a second, that's the radius of the, you see, this is what I'm saying. I find 4D geometry very tricky and a little bit confusing. So that is, I think that might be the radius of the hypersphere. And if that's the case, then we would have to scale all of those numbers down considerably. But initially I was taking that to be the radius of the inner sphere of the hypersphere. So that's, you know, that's why it's good to talk about these things. I've had about 3 or 4 different attempts at calculating that, and I just keep bottling it. So hopefully this time I'll get it right. But it's something like that. Anyway, the main point is that we're dealing with something that is definitely finite, quite large, but definitely finite.
So I wonder whether the volume of the 4D as the 4D topology, does it have a meaning? The volume of 3D has meaning because we have sea length, breadth, and height, whatever. But how do you, because I thought it can flow into each other, like toroid can go into each other and come back. There's a continuity. So how do you find the volume? So does the volume have any meaning in that, you know?
Well, I mean, but you could ask, like, well, does like length and breadth have meaning? I mean, they do, but then if you were, like they do with a physical object, yeah? Then if you rotate, you know, if you call one X, you call one Y, you rotate it, now your X and Y are pointing in different directions. They no longer conform to your concept of length and breadth anymore. So when we talk about, interestingly enough, any matter that exists purely on the sphere, on the surface of the sphere, which we all do according to the model, is in a 3-dimensional space, 3-dimensional surface on a 4D solid, if you will. But with the inclusion of curved space-time, it would imply that the curvature brings you into the 4th dimension. So, so that is the physical interpretation then, and the meaning would be gravity, time dilation, black holes, these kind of things. So it's very, very similar to what Einstein's saying, but also, I would argue, very different as well. It seems like because it isn't, the 4th dimension isn't time; it is an actual spatial dimension.
Yeah.
But the difference is, it's how close are you to the source? You know, that is I think that's the important point. So there's obviously, it's infinite energy at the top because the metric is 0. And also everything's really dense, I think, up there, possibly, as opposed to being very, you know, so it's high energy, all of these things. But also it seems to me that you could have different situations where, for instance, things could be getting, like the metric is contracting. So so large galaxies are actually very small up at the top, you know? And the further you get up, the smaller they get, until the particles, the galaxies at the top could be as small as particles, which could have this kind of loop scenario where what we look at, like what's making up solid matter up here, could be tiny, tiny condensed celestial objects up there, you know? And so, when they're projected out, we're just seeing, like using the James Webb telescope or whatever, when we look at these distant objects, we're actually, in a sense, examining macro-sized subatomic particles. Is a plausible?
So very dense. It will be very dense. You mean dense matter, like black hole?
Yeah. That's actually what they're finding. They're finding, the further they look back into space, they were expecting to find, I think, as those very small galaxies or a very hot, dense universe probably, but they didn't find that because that's impossible, especially in my model with the projection that gets less and less dense as you go out. So I think JWST is proving my model, but also just to be specific, you know, there are these galaxies out there, but they're bigger than they're expecting, a lot bigger, and they're also a lot denser. So, and they can't explain that, but I think plausibly my model could. Also, I think it's interesting because they should have already possibly have thought of this already, and should already know about this model. And I think to some extent they probably do. I mean, you listen to Leonard Susskind, he talks about space being projected from a surface that's all around us. This is the exact same thing as what I'm talking about. And he also talks about how when you get to the largest extent, that should link back to the smallest, and there'd be this kind of, I think he used some sort of analogy to yin yang or something, but I can't remember. So
string theory, right? He says
string theory, smallest. Yeah, well, he's big into string theory, and I'm sure that he would liken it to string theory. I'm not. Yeah, I think string theory could play a part in all of this for sure. So another idea I just had today, like when we're talking about these funnels, you know, that the quasar black hole is at the top of that point. If that were to somehow like move rapidly up, so the actual projection of the quasar were to move rapidly up to the top of the sphere, getting smaller and all, then and if the point goes right to the projection point, then the entrance to the black hole and the exit.
Got frozen. You got frozen, Christopher. Got frozen.
He's been frozen.
Yeah. What happened? He's
Sorry, I got disconnected there, I think.
Oh yeah, you got frozen. Yeah, I mean,
yeah, that was pretty bad. Like just looked, yeah, no problem. So well, yeah, I think the point
you're talking about a quasar.
It becomes a loop. Yeah. Right, the black hole becomes fused with the singularity, the entrance, and so it becomes what I'm calling like a closed loop wormhole, or also you could describe it as like a halo black hole. You know, it's a perfect ring, and so because this can only happen at the zenith point of the sphere, this would imply that if these things happen regularly, for example, there's just like if you go to the farthest extremities of the universe, it will be filled with these closed loop wormhole things flying around the place, but there'd be no way to get inside them. But again, that could link back to string theory, you know, because if these things are very small and they're very far away, or they're very large and very far away, but that equates to being very small and very close, then toroidal black holes, string theory, you know, it all starts to sort of meld together in one concept. We'll see though.
Strong gravity and weak gravity, when it become open strings, like I was saying in the publication, it becomes like weak gravity, and then it loops out, then it becomes strong gravity. So it oscillates between strong gravity and weak gravity somehow.
Oh, okay, and but that is a description is that a description of our current gravity, the gravity itself that we use today?
No, the overall. I mean, the wormhole, for example, we could stretch the string out, and we said that in the vacuum we can stretch the light also, right? So so you can stretch that string out and become weak gravity. So then in that case, if it is weak gravity, then it can flow out. The light can flow out, right? Because now the black hole effect is not there. The black hole effect is the strong gravity aspect. So when it stretches out, now it's no longer pulled in. Now it can easily flow out and can create galaxies. It can just stream galaxies from it, like supernova or other things. Through the
interesting. I don't know. I'll have to think about that a bit more, because I think that well, what you were talking about, I'm like, based on like what I've been doing recently, and the more I look into this, you know, and then I started to realize, oh yeah, okay, gravity, then possibly this other force of weak gravity, and linking it to the end of the universe. So, and then I remembered you talking about gradients between gravity and stuff, and I was like, oh yeah, you know, I think you're getting to what I'm getting to, but from a different perspective. So might not all be making total sense to you yet, but I think it will. I think it's a pretty interesting idea, and yeah.
So another thing I'm talking about is the, you know, you're talking about 4D space, either toroidal or hypersphere. It's an equivalent. Is there an equivalent Euclidean aspect 3D? Like John is saying that it should be Euclidean, actually, in general. So everything kind of you know, collapses back to the Euclidean space, and then you can calculate that. So you can find an equivalence of the 4D space into a 3D you know, Euclidean type thing.
Well, right. I mean, but we live on the tangent space, yeah. So, and that's just all Euclidean. But I guess the hypersphere is all of that information compacted onto the hypersphere. You know, all of the information from the tangent space is up there. But I mean, yeah, I think.
Wait a minute.
It is interesting.
Is time one of your dimensions?
No.
Yeah, that's right. That's what I assumed. Yeah, all your dimensions are space, right?
Yes. Because, well, but there is time dilation.
So I don't know the last comment.
Yeah, there's.
Well,
I mean,
yes,
now, one of the things, John, we are talking about recently that we finally think there are time dimensions, and I'm looking into it. 4-dimensional space, like what Christopher is talking, is geometry. I agree. I just take out his geometry because he's done a lot on that. For the hypersphere, that's you know, space. The time is 6-dimensional. What I'm finding is 6-dimensional based on the clock. So the
well,
clock,
that's
you know,
Christian's idea of 6-dimensional space, and then your idea of 6-dimensional time seems to go together.
Yeah, and then your idea of 4-dimensional space. So,
but then what would that be? That would be 60-dimensional universe or something. Yeah, I mean, it's a really cool idea. I'm just not sure I'm entirely sure how it works.
The idea of dimension is that there are different clocks. So that's what I'm working on. I think the clocks will give more physics of it, the gauge.
Yeah.
Clock is a time gauge after all. So I'm saying that I have one clock, then we are going together. We have, so that's, I call it individual or whatever, the self clock or bio clock, biological clock, whatever, or the mind clock. The mind is going. And then we have a group that's called communication clock. I call it communication clock, which could be much faster because the communication could occur by gravity. So it could be faster than the mind clock.
I don't know about that though. I see what you're getting at, but yeah, I think that's a hard sell though, isn't it? In the physics realm.
Yeah, I'm looking at but the thing is that the instinct. You know, I'm talking about the thought and the instinct. The thought is much slower than the instinct. Instinct
well, you know, I mean, there was a time when scientists kind of balked at the idea of attempting to discuss or explain consciousness or anything like that.
Yeah,
but I think those days are over. So, you know, but if you are going to go that route, you know, you need to be very knowledgeable in a lot of different fields like neuroscience and. But
I am looking into that a little bit more.
You could also come at it from another angle. Like, for instance, I'm not very well versed in things like forces or these kind of equations, but nevertheless, I know quite a bit about hyper or different dimensional geometries. So you can kind of come at it from a different point of view. Like you could start. Certainly with I know philosophy and physics are generally
that's what I did more. Metaphysics. I did more metaphysics than physics.
I think if you could do that, but it's you know, it's a really difficult thing to try
So,
and do.
you know, I see it from the metaphysics. I can see much more clearly because I do yoga, meditation. I can naturally do it. I am natural meditator, natural yoga. You know, I can.
All right. Did you recognize
form.
the guy on the cylinder then?
Yeah, but convert that metaphysics into physics.
The guy, was it Swami? The guy,
oh, that's Swami Vivekananda. Yeah.
Yeah,
That's an interesting one. Yeah, I was about to say that. It's an interesting one because he knew about the mind. He was looking at the mind, what mind is, things like that, you know. And he has gone deeper and deeper into the aspect of the very mind itself. What is mind? You know, I think he understood some and associated with consciousness, things like that.
Yeah.
His guru was in India called Bengal, Kolkata. His name is, his guru was Ramakrishna, Paramahamsa. But he never traveled. His disciple, Vivekananda, Swami Vivekananda, he traveled to US, various places. But he finally, he had a problem. I don't know, with the brain aneurysm or something. So he died fairly young. But he was thinking about the mind, and I was thinking, the whole aspect of the mind itself, and he was trying to fit into the, into philosophy of Advaita and all those things, which is very deep aspect of spirituality, about God, about are they like God and devil, or is it all one? Advaita says everything is one. Advaita means there's God and devil, So that aspect, for example, somebody called Shankaracharya, who's very similar to the one German person who did, I forgot his name, but he was very similar to
Nietzsche. Oh.
Yeah, somebody. If I hear the name, I know immediately.
There's all these people, Kant and Schopenhauer, and
some Saxon sage. He was very high level sage of Saxons or German, and they are very similar. They are separated by distance, but their thinking is very similar. Lutheran and all came later, I think, but it was somebody else.
Okay.
It was much before Lutheran, I think.
All right. Lutheran. Well, if you think about it, let me know.
Yeah. So it's an interesting thing because I thought about very deep in that sphere. So I did see the revelation, I did see the consciousness, but I couldn't translate to physics. That's what I'm trying to do. So if I go there in that sphere, I know that's correct. I have no doubt about that. But how do you describe the physics? The only question. So I think the closest thing I can think of right now is clock. I have to still work on it. The clock thing is a very good thing because you can actually measure it. And I like the fact that you can measure it. Because many other things are mathematical. It's a hand-waving thing. You can say this way, that way. But if you can actually measure it, you are actually proving it in a way, So that is enough. For physics, proof is necessary, right? A proof is in the observation. You have to be able to observe and measure. And that's the whole problem. How do you really measure it? But I think the clock idea for me is that there is a mind clock of individual. There is a communication clock among people. And there is like Einstein. You remember Einstein was looking at with a Planck in Germany when he met him first time, a clock like Uncle Ben. So that is like the global clock. And the cosmic clock is much further than that. So you can draw a picture. I'm here. The communication clock, people are sitting here. That's a communication. Then you go up there, that's a global clock. And further down is the cosmic clock. So in terms of rotation, it's interesting. I find, and I have to still think about it. You may think, I'm looking here, right? That's a real thing. But what is at the back of me? That's actually, I call it dark clock. Dark matter, okay? And the communication clock can actually face to me or face against me, okay? So they have, okay? So these are the details I'm going through. I think it makes sense. So one person, the communication clock, is looking at me, but he does not know the other side. Actually, Einstein was looking at the other side. He was looking at the global clock.
Is this like how people can like become how miscommunication can happen or something like?
Yeah, and so Oppenheimer, for example, may be like me. I mean, or I am like Oppenheimer in some ways. Oppenheimer could see all the clocks, whereas Einstein was looking at the global clock and the cosmic clock. But he did, he could understand. So from him, he was looking at the back. So he was looking at the back of, Oppenheimer was looking at Einstein, but Einstein was ahead. So Einstein is looking like this. So Einstein couldn't see Oppenheimer, but Oppenheimer could see the back of Einstein, something like that. So the clock analogy, if we expand that, you can explain a lot of the things in the proper perspective. But the workout is quite complex. The math is qualitative, right? But math is quite complex. That's the only product. The working out the network is like working that.
That's the fun part as well, isn't it, Rajan? That can be a fun part. Sometimes it can be frustrating if you keep getting the wrong answer, like I was saying.
And then you mentioned a black hole. Black hole is above that. That's a real clock, surprisingly. That's the strange thing I come up with. The black hole is the real-time clock. The real clock is the black hole. See, is the black hole is the one that's keeping us? Is the eye of the black hole is looking at us? Is it controlling us? That's an interesting thing. That's interesting. The black hole may be up there controlling us. It's looking at us. Oh, so it's kind of moving us, and it's controlling all the other clocks in some ways.
All right.
And like Gerd said, Gerd said we are in a black hole, right?
This point I'll have to go soon, but I just want to say that the point at the top of the sphere, which is like the projection point, is it's kind of like it reminds me of some of Chris Langan's work, if you've looked into the CTMU yet. And Chris Langan's, again, he's kind of metaphysics, but he merges physics with metaphysics and maths. And so it's a very dense kind of system. It's very interesting. And I think he solves a lot of the sort of metaphysical issues, through these things called telons, where you have a physical, I think there's tertiary, secondary, and primary telons or something like that. So like a table is a secondary telon. It participates somewhat in its own existence, but it doesn't have the ability to like change anything like we do. So we're like, are we tertiary telons or primary telons or something like that? We're like, we participate in our own existence. We're made of matter, like the table is, but we're also able to, interpret that in some way through consciousness and self-consciousness. And same with animals, maybe a bit lower than us, but then he would have God as the highest talon, talis unbounded or something. But God is looking at himself, like, which is matter and us, but. So he sees everything, and he's saying like, so this is going back to the concept of like the all-seeing eye or something, and he's saying that if God cannot see you, I don't know how he said it, but essentially what he's saying is that and this is the point that I'm getting from my model, so maybe it's my thought that I'm projecting onto him, but either way, I'm pretty sure he agrees with me on this, that the only thing that can exist in the universe is that which can be seen by the projected point. If it's not seen by it, it does not exist. And I think that he would say the same thing, that if God cannot see you, that if he's not looking at you, you simply don't exist.
Yeah. So that's a clock and consciousness. There's a lot of connection. So I think it's all, and also I think it's black box. If you see, my general transform says the all units are black box. Black hole is an instance of a black box. Black box is more general thing. So there could be a black box within the black box, another black box within the thing, and that's what a black hole is. So when you have black box here and black box inside, the black hole is the one that the deepest thing inside. So I think the idea of that that we can understand everything may be questionable, because If it is all black box, we are just interpreting what we can see, but there may be more things that we can never figure out. Maybe just mathematics. So that's conclusion. But based on the information we get, you know, a time is created within us. Based on that, we can interpret something. That's all we can do. So we have to be, I feel humble. I feel humbled by the fact that God is giving us all this information, but he's ensuring that we don't get the last one. You know, that's the feeling I have. We won't get the last key, the last information, and by that time, we may all disappear. Right.
Oh, well, that's true. That's very true. But I kind of feel like now with this information that, like you're saying, you know, I think it could explain a lot, and I think it does explain quite a bit. So obviously our universe is the tangent space, which is flat. Then we have this curved hypersphere as well, which also seems to create the sense of perspective, you know. So when you look out into the world and things are smaller, the further away they are from you, even though that's a byproduct of our killer vision, which in some sense is a fractal representation of the entire universe in a sense. So there's that, because like things will get smaller as they go up the hypersphere. So when you look out into the world and you see things getting smaller, that is in a sense a bit like looking into the fourth dimension already, the fourth spatial dimension, I mean. So but then we have to notice that this hypersphere is embedded in a much larger space, which is infinite as well, possibly, unless there are projections within projections within projections, which is very possible. And then if we wanted to bring time into it from a, you know, as a direction point of view, like a Galilean, I don't think you can do Galilean relativity, that kind of thing. I mean, you kind of can, yeah, but ultimately you kind of have this thing where you have like spheres within spheres within spheres of the previous moment. And I think the way Susskind's going about that is to say that, well, on the surface of this vast de Sitter space, we have the holographic. So like all of the information that is contained within the universe is essentially pasted onto this surface. But it's not just the information of what's in the universe now, it's what's will be in the universe and what has always been in the universe. It's all just like diffracted onto the surface of this sphere. So, and that's not true of my model. I don't think that the point at the projective point does not, I mean, it could contain all information about the universe, but there's no reason to suspect that it does based on the model. Whereas if it was if the model was like pointing to holographic principles and saying, yeah, that's totally true, there's no getting away from it, then you would have to accept that all of time and space are contained within the projective point. But that's just not, we just can't do that from, although what is true, yeah. Well, just one.
Seems your model.
Just one last point. There's all of us in this universe, yeah, all of us sitting here and everything can be traced back to that point. So we all exist in the same point, you know, in four-dimensional space. We are all connected, like very, very much. So that's pretty cool. We are basically all the same thing here, and yeah, and also
it seems your model is a little sensitive.
To what?
Sorry about that. It seems your model is a little sensitive on where you pick your 0 point.
Oh, yeah. Well, I can interpret that one way. What do you mean?
Yeah, you picked it as either what? The center of the Earth, if I recall right, or the center of our galaxy? Suppose you pick it at another point.
Yeah. Okay. Well, why would I do that?
Say move the bottom center point. Now you've got a lot of, anisotropy, I think you called it.
Yes.
Asymmetric behavior of some of those things. Like, remember, you had one galaxy and had a lot over here and fewer over there and almost none vertical.
Well, I think the anisotropies were to do with
suppose you were to
with spheres, concentric spheres of galaxies, or
yeah, the way that laid out. Right. Suppose you were to pick the point, not in our galaxy, but the center of our galaxy cluster.
Okay.
I mean, our galaxy is in a galaxy cluster, roughly what, 10 megaparsecs in diameter? Or something like that.
Okay. Yeah. So then
suppose you pick at the center of that.
Okay.
But then you see, then it would look like a little bubble. And then the, let's see, the Virgo cluster, which was one of your points you pointed out. I forget what you made. I forget what you called that direction. Like the CMB is in that direction.
Oh,
the great right, and then the other side is the Hercules cluster. And if you pick the point at the center of our galaxy cluster, then those two things also appear to be little balls.
It's not Magellanic, right? It's not Magellanic.
Yeah, I'm thinking
Magellanic.
that if he picks the center someplace else.
Well, this is it. I mean,
it's like the nebula, the Magellanic cloud or nebula, something like that. No, Magellanic.
Nebula refers to stars, I guess.
Yeah, but just to get back to your point there, I mean, Gerd had this issue as well. I think he was commenting on one of the papers I wrote and saying, you know, there is no. I was suggesting that the Earth is at a significant geometric point. I was saying in the universe. There's also another significant geometric point, which is where the light is, you know, where the projected point is. And that's completely opposite to where we are, I'm suggesting. Right. But then, yeah, so we went back and forth on that issue. And he says that there is no significant geometric point. And that is perfectly valid. Like, if you were to move away from the Earth in any direction, and if the hypersphere rotates with you as you move, let's say, or the tangent space rotates, then it will appear like you're still the center of the universe, and everything is moving away from you at light speed or whatever, 4 times light speed. So from that perspective, yeah, we're back to a situation that
you see that's not true. If all you look at is just distances and direction, which is what you did, right? You only use distance and direction to locate where your points were. If you do only that, then you end up with a highly clumped structure. And we, meaning our galaxy, is on the outskirts of a galaxy cluster, several galaxies. And those others are within 10 milliparsecs of us. And then if you go in the direction of Virgo, you end up with a gap of roughly 10 megaparsecs to get to the Virgo cluster, which is then a really big cluster. You go in the other direction, you end up with Hercules, and that's the anisotrope you see in the CMB microwave background map. You know, the hot point and the cold point and all that stuff.
Yeah, yeah. No, you're making a good point because, yeah, go on.
But in that direction of the center of our galaxy cluster, and at small angles out from that are close galaxies. But go in the opposite direction, and you will find there's this big gap before you start getting to another galaxy cluster, which is the anisotropy that I think you were seeing.
But I mean, you know, the way that do you I mean, you know, I don't know. I find this a bit confusing myself because I'm listening to your points and I'm thinking, yeah, that like I wrote another paper where I tried to fill in the gaps in the STS data using various methods, including like an artificial neural network. And the point of it was to show that the great walls in the data, these concentric circles, actually do join up and are fully surrounding the Earth. And I did that because I noticed, so I wanted a computer to do it because I wanted it to be unbiased, you know, so that I didn't put in where the stars were. Because then if we look at other physicists, they say, well, here's the map of the universe. And then, you know, it's like wall here, and then it goes, you know, and it goes down here, you know, so they try and make it as chaotic as possible. And the same with these big models that they spend loads of time and energy and put like huge amounts of computing power into to create these global lambda, you know, these ones with the cold dark matter lambda models, and Christians always giving out about them because they have to put in like 70% of the, they have to put it in as a raw figure. They just type it in, you know, it's not based on any maths, not based on anything. They just enter it and then hit play. And then what you get are all these galactic filaments, and it looks really impressive and beautiful. But what you've lost is all of the structure that comes directly from our observations of the universe, with these concentric shells around our position. And again, everything just looks like a big mess, like a very beautiful mess, but still, like the structure that they're trying to describe is gone. Like if you were to place the model that I just showed you, or, you know, the map that I showed you against their model, there's no comparison. Like all of the details of the model have now been destroyed. They're all gone. So, I mean, I'm a bit concerned though, because I would say that the distance from the Milky Way to the first Great Wall, according to I could be wrong about my measurements because I'm getting them from other sources, and indeed a lot of these things could be incorrect. I could have interpreted it incorrectly or whatever, but it seems to me that that is around 1,000 or 1,265 megaparsecs if you use a Hubble constant of 70, flat universe, and you're looking at angular distance. So, but I don't think, and the Great Wall is a good bit further out, but there's a huge, vast area of almost nothingness between, you know, either the Milky Way and that area, or our local cluster in that area. But either way, it seems like there is a big empty void there, which is interesting because in the black hole model, you know, they're saying, well, we know that everything is expanding away from everything else and that there was no one point of explosion, because if there was, then we'd be able to look into the sky and see this big empty hole where everything had emerged from. And I'm saying, yeah, we can find that. That's where we are. We are the point of emergence. Now, why would I place the Earth at the center of the, or you could say galactocenter, you could place the Milky Way at the center, but then, and that seems reasonable because of the anisotropies that I've clearly shown are present within the universe, and that people who are trying to create other models are covering up for various reasons, for their own purposes, let's be honest. And then, but then why would you place the Earth?
That's what I was trying to say.
Yeah. Well, wait a second. So the anisotropy then of the cosmic microwave background is the second sort of piece to this puzzle, and the final reason why you might put the Earth in the center rather than anything else is because the Earth is aligned. The the plane of the ecliptic of the Earth and the plane, the equinox points are aligned with the dipole of the CMB, and that's just not possible, like by chance. So that's just ridiculous. So that's why I'd say you put them there. That would be my answer to that.
Well, there is another reason that might happen.
Well, I mean, of course, you could say that.
What is redshift? If redshift is related to velocity at all.
What? If redshift, sorry, is related to what?
If redshift is related to velocity at all, then you're going to see the dipole of, say again?
Oh, yeah. So
if redshift is related to velocity, meaning the Doppler shift, then all of a sudden you're going to get the CMB.
Yeah, but that's
the other way you can get that.
That doesn't explain why it would be aligned. That doesn't explain why it would be aligned with the. That does explain like something, but it doesn't explain the alignment. Is what I'm talking about. So that's a different issue. But anyway, you have to suppose a velocity there.
Yeah.
So I'm saying it doesn't exist because the Earth isn't moving. Like that's clearly the issue there.
No, but also if you're comparing to the Earth, then.
Well, there was another paper by an Indian guy who showed that the anisotropy of the cosmic background radiation is not due to the acceleration of the Earth because it doesn't fit with the acceleration. It's like either too much or too less, too little. You know, so the two things don't match up. Yeah. Anyway, so those are the reasons why I would place the Earth at the center, because it just makes the most sense. It fits the data the best.
But the whole solar system, I think, is the evolution. It's just the Andromeda and
all over the place.
Yeah, Milky Way and the Andromeda somehow collided and produced the panhandle where the solar system is. It's quite possible, and then it is emerging from that, something like that. It may be a dynamic effect rather than a static effect that Earth is there.
I mean,
dynamic collision of galaxies.
But you'd have to have the universe, therefore, is now like rotating around the Earth, in the model, I'm supposing. And then you can look at the speeds necessary to do that. I don't know. I've calculated it, but I don't have the figures. But you have to go like quite a far distance out before things that are rotating reach the speed of light. But comparatively to the size of the universe, it's next door, So, but then you go out again, and they're 2 times the speed of light, 3 times, so they're going really, really fast. But all of that can be explained again because of the hypersphere and the exponential metric on that. But the calculations need to be done to show that, one can offset the other, that because the speed of light is traveling at 4 times the speed of light out there, that everything seems normal to them while they're out there, and so forth. So that's not a problem. But yeah, I mean, there could be I mean, obviously there is general relativity as well, which says that because you can't know which is moving, so the Earth could be rotating and the stars are static, or the other way around, and both are equally valid reference frames. So,
but the Earth is much younger compared to the the universe. But
well, I mean, this is it. I mean, they're looking at
the universe.
Well, yeah, but if they're looking at what is this? They said the universe is 3.8 billion years old, and then recently another guy
14,
said, "Well,
right? What is it? 14? What is that? 14?
Sorry, what did I say? I mean, 13.8 billion years.
13.8. Yeah.
Yeah. I think I said 3.8. So, and then another guy wrote a paper there recently. I've forgotten his name now. I think he's an Indian guy. But he's looking at the results of the galaxies from the James Webb telescope. And he's saying that there's no way that these could have formed in 13.8 billion years. Like they're too fully formed based on our models. So he's suggesting, well, we push it back. I think they said 26 point something billion years. So basically double the age of the universe overnight. Yeah, I mean, so these are issues like, there could be different things going on, especially at the beginning of the universe. There's a lot that we don't know about. I'm suggesting that there is no singularity anyway, but was the Earth
no Big Bang? No Big Bang then.
Well, there was the Big Bang, like everything was in the center and then it was projected out into the universe. Like that actually happened. So And from the perspective of inside the tangent space, that's just going to look like something going oof, like that, you know, off to infinity. So that's a massive acceleration going on. But was the Earth present in the center of that at the time? Well, we don't know if that is true or not. Did it wind up there sometime afterwards? But I believe that there is some evidence to suggest that it must have.
Let me ask first.
Yes.
Let me ask then, do you accept a fixed reference frame, meaning there is such a thing as a reference frame for the universe?
Oh, like a rest frame for the universe?
I'm not too sure I'm asking it correctly.
Well, currently in cosmology, they consider the cosmic microwave background radiation to be the rest frame of the universe. And the anisotropy that's being brought into it is as a result of our motion through the rest frame. There's a lot of issues with that, not least the fact that the anisotropy doesn't match up with our motion through the universe. And then a whole host of other things that other people have raised that really isn't my area of expertise, really. But yeah, do I accept a rest frame for the universe? I'm not sure if it's. I mean, it's not hugely important issue for my research. I mean, the tangent plane is at rest.
No, but you have to pick a center. In your research, you have to pick a center.
Well, I don't have to. No, I did explain that if the tangent plane moves as you move up the sphere, everything's going to appear to be the center. So that's equivalent to the model that we already have.
You still have to pick a zero someplace.
No.
But you still have to pick a zero someplace.
Well, maybe you do. I mean, it's an interesting.
Yeah, suppose you were to change the zero to something. What changes in your model?
Yeah, that's a good question. Let me think. Okay, so if we were to travel in one direction for like a couple of hundred parsecs or megaparsecs or whatever, then what's happening in my, so as it stands in the model that we have, this is the logic I'm going. So we're on Earth, we look out and everything appears redshifted around us. And the further we look, the more redshifted it is. That is because of the projection from the top of the hypersphere. But if we were to move,
okay, no.
But if we were to move up the side of the hypersphere and get closer to the projection point, we're going to have this Mobius transformation, which will cause a massive anisotropy in the universe. And then from that position, our new position looking out at the universe, in one direction we will see everything redshifted, and the other direction, the other half of the universe would appear blue shifted. So, and we would also start noticing other deformations, and very quickly we'd be able to tell, okay, Earth or like our galaxy is really like a central thing. So if there were alien astronomers out there, they'd all know to come here pretty quickly, which is probably why there's so much activity in the skies and they're interested in our military. They'd also be scared shitless of us, excuse the language, because why are we so important? What the heck why are we at like the center of everything? So they wouldn't want to necessarily like come and talk to us. They'd be like, we're just going to sit and observe and see what happens next. But
so what did you just explain what your model of redshift was? I mean, you said as you moved up the side of the hypersphere, the redshift changes. Remember I said that there's two ways. Model of redshift?
Well, there's two ways that it could play out. Like one is that I just described, but the other is if the metric moves as you move. You know, if the metric on the sphere tilts as you move up the sphere, and the point moves, the projective point moves, then you will always be at the center of the universe from your perspective. But that was the original model was called the unique hyperspheric model, So everyone has their own unique hypersphere that they drag around with them. But I don't know. So that's another possibility. But there's issues there, obviously. But I mean,
so that'd be more like multiverse. You're talking about multiverse.
Possibly. Yeah, but obviously, whatever that is, whatever those like, if we all have our own personal little bubbles that we walk around with, then that's got to reference something else. And what is that something else? And how is it positioned? And how is it being projected? So it just raises more questions than it answers. And it's, but I do like part of it.
That's an interesting. It's an interesting metaphysics kind of thing.
What is? Of the idea that everyone has.
Well, the idea that we're all the center of something, you know.
Oh yeah, well.
Because
I mean, that would be true.
You get into the idea of.
But you know, if you've got the tangent space, that's going to infinity. So where you are, you know, the universe is infinite around you. Where I am, the universe is infinite around me. So from that perspective, we are all at the center, you know, of the universe. But I think on another level, then there's actual centers. Like there's the center of the hypersphere. That's not in our universe. And then there's, you know, that's a point outside of our universe. But all of these points are just as important as like where we are, or even more important. And certainly the top of the sphere would be, if that didn't exist, then nothing would exist. So doesn't.
So that would be a black hole, right?
But as you change the center.
So yeah, so then, I mean, if we all had these unique spheres, and then you could drag them around. I kind of like that because it reminds me of like zorbing in the ocean or something, and the ball tilts slightly. So you're trying to move in a direction, the ball starts to tilt, therefore the metric tilts, and therefore you have this kind of general relativity issue with, you know, time dilation and stuff. So, but ultimately, after thinking about that for a long time, I abandoned it because I found it just to be a bit messy. And I'm moving down the road of like the cleanest, sort of purest, but at the end of the day, it's no longer that clean because I'm talking about now a bumpy sphere with spikes in it, and so it's getting a bit more messy. But I think the benefits are outweighing whatever imperfections are now being imposed upon the model in terms of explanatory power. Well, in terms of explanatory power for Holton Arp's work with the galaxies and the redshifted quasars, it is probably the only
part of Arp's work included what were called periodic redshifts.
Oh yeah, quantized redshifts or something.
Remember that? Say?
Yeah, that's very interesting.
Well, yeah, that term has kind of changed over the decade. It used to be quantized redshift. Oh. It's now periodic redshift, I see.
Yes,
but the term has changed, but the data is the same.
Right. Yeah, yes. I remember hearing about periodic redshift going back for a long time, yeah. So it must have changed a good while ago. But
like cycling.
Much better. Quantized redshift, you hear it, you instantly know what it is. Periodic redshift, that could be fucking anything. Excuse the language, actually. But just to
cyclic. I mean, it may mean cyclic.
It doesn't even mean cyclic because the thing is constantly building anyway. You know, it's like it goes 0.3, 0.6, 0.9. You know, although I'm not exactly sure. I'm assuming that it's building in roughly about 0.03. Just keep adding 0.03, but I don't know. There might be some other. Well, I suppose, you know, sequence is the word I'm looking for rather than period.
Even the periodic redshift, could it be contraction and expansion going on?
Well, this is it. There's a guy called Hirano, I think, who's also worked on these kind of things, and they were among some of the people who noticed these walls, you know, in the data. I forgot what they refer to them as, but they probably use something anyway. But so the Great Walls, and they said, well, one way to explain this is that the universe was expanding, then contracting, and then expanding and contracting. So it creates waves in the galaxies that appear to go out from our position. But I would dispute that as an explanation, although I do like it. But because if that's happening at every point in the universe at the same rate, or even at different rates, that would be even worse. But let's say at the same rate, then we have expansion, contraction of every point. So the stars will all just, there will be a massive interference pattern. And so the sky wouldn't have these waves. It would just be, it would have a completely different structure. I mean, you could argue that maybe that you wouldn't be able to see that because you're at the center of your own expansion bubble, but I would just disagree. I just don't see how you could, because the whole reason for saying that the universe is all expanding is to explain away the fact that we appear to be at the center of the universe based on the fact that everything is redshift away from us. So now that we have these waves within the galaxies, well, that is an anisotropy that needs to be explained away, because otherwise it definitely says that we are at the center of the universe. So then we bring in the contraction expansion model, but I think that just doesn't save you, because it would just create all of this interference with the galaxies. And
I think the density matrix.
I was addressing this idea of changing the center had to do with another observation, which they call the fingers of God.
Oh yeah,
have you ever heard of that? That's another that's another ARP thing, where it appears that no matter where you look, you know, the redshift indicates that it's pointed towards us.
Well, yeah, the fingers of God. Yeah, there's another researcher who talks about that and says, well, they do look, but you can explain that using relativity or something, and that's
well,
not
as far as I know, nobody's explained it except me. But then, you know, that's another.
Well, that is true. I mean, I think you know, because this model.
But if you were to change.
Sorry, go on.
If you were to change their center, the center of where you start from zero at to someplace else, then you should start to see funny things happening until you change to a center where the anisotropies disappear. See, that's a similar situation to the Ptolemaic versus Copernican solar system. When you change the center to the sun, things got simpler.
Yeah, that's not true of the Tycho Brahe method, though, which was actually, you know, in between the two models and just as equally valid. It's actually the one that we use to launch spaceships.
Very more like vortex.
Well,
vortex model.
Yeah, because we use the Earth as the center of the universe. NASA does.
You remember? Well, you remember historically, the Ptolemaic model was not rejected until the 1800s.
Wait a second, is that
scientific?
Like epicycles and all that?
Ptolemaic model was epicycles, and its advantage was it was accurate, more accurate than Copernican, or, well, you said Tycho Brahe. That's, I don't know. That's what's his name? Somebody else. His student's name.
The Tychonian model of the universe is just as simple as the Copernican model. You know,
the what is?
But it's just the same. You just have like the Earth not moving and everything moving around it, but you don't have any epicycles. You just have the sun is moving around the Earth, and all the bodies are moving around the sun, and it just works. There's no.
Yeah,
look into it.
But that wasn't accurate.
No, it is accurate. It's perfectly accurate. In fact, it's the one that they actually use for them to go into space. Yeah. Or well, if they don't, they should be using it because it's far better. Well, they must use it because when they launch a rocket, they have Earth as the center of the system. They don't model it with the sun as the center and the Earth moving and then calculate from a moving Earth. They calculate from a motionless Earth and all the moving bodies. And they don't use epicycles, so they must use the Tycho Brahe method, Tychonian model. And if they're not doing that, then I don't know what they're doing. Like, maybe they're not going up there at all. I don't know. I'm just joking.
They're using what the post, what's it, PPN, post something or other, Newtonian or something like that, which starts with the Earth, right? And then starts applying force.
Oh, okay, yeah, well,
whatever.
Yeah, like I say anyway, that if you look into the Tychonian model, it's just incredibly, I mean, it's a lot simpler than what you just described there anyway.
They used to use a North Star, telemetry with North Star or something. Was it? They use that? Because
I don't know.
The ships, the people who went by ships, they used to use North Star as a guiding point for, guide them to the place. So I don't know whether they're using the same thing with the space. Because
no,
that's the compass.
I'd say that once you're off the Earth,
telemetry, right? It's part of telemetry, isn't it?
I mean, maybe. Yeah, I don't know. I've never heard of it though.
The GPS system, all that.
Yeah. Okay, guys, I better go anyway. I'm fading.
Yeah, it's a good time to. Yeah. So we'll see next week. I think we'll have a lot to think about. And one thing you want to just resolve, and you can think about it. Emmanouil mentioned about Dr. Andreas.
Will I end the stream anyway, or?
Yeah, I mean, Andreas gives yeah. So we want to find out when is a good time.
What is this, Malaver? Dr. Malaver and Emery Taylor, did you mention?
No, Emmanouil. Emmanouil mentioned about Andreas Gimsa, the German guy.
Oh, I didn't hear about this.
You see the email he sent?
No. Or if I did, I didn't.
Okay. Andreas Gimsa. Andreas Gimsa. Gimsa. I think Gimsa.
Okay.
So
and what about it? Is he?
Yeah, he talks about the gravity and all that things. I think he's in the RG. He has RG. So you may want to look into it. So, and Emmanouil was telling me whether we can schedule so he can present it. Maybe this month or next month. We can think about next week.
Oh, right. So, Emmanouil, Markoulakis.
Yeah, Emmanouil Markoulakis. Yeah.
Oh, okay. I did not get that email, no. But yeah, I mean, of course, if he wants to present something, or this other person, whoever. Would that be next week, would it?
No, next week. We have to schedule it, and then we ask whether it's okay for them. So we will discuss next week. I thought, and then we'll either this month or next month we can schedule some time and ask whether that's good for you.
Great. Okay. See you then. Bye.
See you. Have a nice